So in question 4, we have to calculate the common acceleration and the tension in the string when the system starts to move. So we'll start off by drawing in some forces. So we have the weight of the block, which is 12g. We have the normal reaction here. Now it's a smooth plane, so no friction. We do need to draw in this tension force here. And then for the second object, we've got a weight of 7g, tension here. And let's assume that when the system is released, the 12 kilogram block slides down the slope and the 7 kilogram block moves upwards like so. So I'm going to draw in the components of the weight like that. It's 40 degrees. So there's my right angle, so that's 12g sine 40, 12g cos 40. And then if we look at the 12 kilogram block, I'm going to say that down the slope like that is positive. And remember, throughout all this, we're using the resultant force is the mass multiplied by the acceleration. So down the slope, we have 12g sine 40, that's positive. T going up the slope, so negative, and that equals 12a. And then for the 7 kilogram block, I'm going to say up is positive. So I've got T minus 7g equals 7a, and we have a pair of simultaneous equations. And the easiest way of solving these is to add these together. So we've got 12g sine 40 minus 7g equals 19a, and from here we can work out the acceleration and then substitute that back into equation 2. Or equation 1, it doesn't really make any difference, a bit easier to sub into equation 2 and use that to calculate the tension force. So that gives me these two values, which at the very end I will round the acceleration 0.37 meters per second squared and the tension 71.2 newtons. So here are my final answers. So question number 6, we have a crate of 30 kilograms, so that's got a weight of 30g, and it's being pulled up a smooth slope inclined at 30 degrees to the horizontal by a rope which is parallel to the slope. So there must be a tension in this rope, and then we must have a normal reaction force like that. The acceleration is 0.75 meters per second up the slope. So part 1 requires us to sketch the diagram, which is there. Resolve the forces in directions parallel and perpendicular to the slope. Well, it's the weight that needs to be resolved in directions parallel and perpendicular to the slope. So we know that this angle here is 30 degrees. So that component there, 30g sine 30, 30g cos 30. So if we were going to resolve the forces, I could say the I component goes up the slope, J component goes off the slope. Then the normal reaction in its vector form would be 0 nr. The tension would be T0, and the weight would be minus 30g sine 30 minus 30g cos 30. So those are the resolutions. So part 3 requires us to find the tension in the rope. So we're using F equals ma. Now I'm only really interested in what happens parallel to the slope, because perpendicular to the slope the forces will be balanced. So this normal reaction is balanced by this component of the weight. They're equal to each other. It's not that interesting. But if we resolve the forces going up the slope, we've got tension minus 30g sine 30. So I'm now looking at this, which is negative, and this, which is positive. They create the resultant force, which is equal to the mass 30 multiplied by the acceleration, which is 0.75, and we rearrange this to find out t. And that comes to 169.5 newtons. And worthwhile noting as well that here we could have said normal reaction J, tension I, and here we could have said minus 30g sine 30I and minus 30g cos 30j as well. So in part 4 of the question, the rope suddenly snaps. What happens to the crate? Well, there's nothing pulling the crate up the slope anymore, but it still has momentum. It's got mass, it had velocity, so it's going to continue moving up the slope until it basically decelerates to a halt. Its velocity will then be 0. It then instantaneously changes direction and starts sliding down the slope. So it will continue moving up the slope with its momentum, but it will be decelerating until its velocity is 0. It then instantaneously changes direction and then starts sliding back down the slope. So in question 7, we have 2 toy trucks connected and travelling down a slope. So let's draw on the acceleration and its direction there. The slope is inclined at an angle of 5 degrees to the horizontal. Now we know the mass of these toy trucks. A has a mass of 6 kilograms, so a weight of 6g. B has a mass of 4 kilograms, so a weight of 4g. There's a reaction force here for A and a reaction force here for B. Different reaction forces, so we label them differently. That's important. And the forces are connected by a tow bar. So let's put on a tension here and a tension here. So these tension forces are equal. One of them acts on A and one of them acts on B. And I'm assuming those are the directions of the forces acting on A and B. We don't know that, but it's okay. All that will happen is if we've got the directions wrong, we'll get a negative value of t, and then that will give us some information about the actual direction of t later on. So I'm going to draw in the components to each weight, like that and like that. So remember, these angles are the same as the angles of the slope, here and here. And what we're going to do is we're going to apply F equals ma, taking down as the positive direction. So we're interested in what's going on parallel to the slope. So forces that we have acting parallel to the slope, we've got these T forces, these red resistance forces here, and these pink components here. Now let's just make sure we know what those pink components are. So this is 6g sine 5, and this one is 4g sine 5. So what I'm going to first of all do is look at the forces on truck A. So down the slope I have 6g sine 5, and then T and 2.5 are up the slope, so that's positive, and that equals mass 6 multiplied by the acceleration A. We don't know the value of that yet. So we've got one part of a simultaneous equation. Let's do the same for B. This time we have 4g sine 5, and we have T directed down the slope, so that's plus T, minus 1.5 as that's up the slope, and that equals 4a. So we have our pair of simultaneous equations 1 and 2, and as is often the case in these situations, you have a minus T and a plus T, so it's easy to actually just add the two forces together. So we then get 10g sine 5 minus 4 equals 10a. This then allows us to work out the acceleration, which comes to, and the acceleration works out to be 0.4541 meters per second squared, which we're going to store in calculator memory A. We're not going to round it, as we weren't required to do that. So the two things that we need to calculate, one of which is the speed of the trucks after 3 seconds. So using our SUVAT information, we need to calculate V. Rule out the S here. V equals U plus AT. Substituting in the information that we have gives us the velocity here, which is 3.36 meters per second to 3SF. Now, going back to our simultaneous equations over here and here, we're going to use equation 2 to work out what T is, remembering that in this context, T is the force acting on either particle A or either particle B. So this gives me T equals 4a plus 1.5 minus 4g sine 5. Let's use our calculator to work that out. Now this comes to minus 0.1 newtons, which means that the direction of the forces acting on the particles, we have not got that correct. So what actually happens is the force T pushing on A should be like this. Let me highlight it in a different colour so it's clear. So that's the force T acting on A and the force T acting on B, and T would equal 0.1 newtons. So those are the forces on the particles, on the trucks A and B. If we're actually looking at the forces inside the rod itself, then there'll be an equal and opposite force here and an equal and opposite force. So the forces inside the rod look like this. And of course, they're both equal to 0.1 newtons each, and they balance each other out. So look at the direction of those forces. They're pushing inwards. Think about if you push inwards in both directions on an object, you're squashing it, so it's in compression, it's not in tension. Tension would have the pink arrows reversed and they would be pulling it and stretching it. So in question 8, we have a pair of connected particles, a trailer and a car, connected to each other like this. The car has a mass of 1,000 kilograms, so a weight of 1,000 g. The trailer has a weight of 250 g. There's a normal reaction acting on the car and there's a normal reaction acting on the trailer, like that. Now, the driving force of the engine of the car is 2,500 newtons, and there are resistances to the motion of both the car, 700 newtons, and the trailer, 300 newtons, like so. Now, there are forces acting due to the tow bar connecting the trailer and the car. We've got a tension force here and a tension force here. And again, we're not going to worry about the directions of those forces. If they turn out to have been in the other direction, it doesn't really matter. This will still work. So we know that the car is towing the trailer along the slope, so let's say acceleration in this direction here. Now we must draw in the components of the weight each time, so these orange components here and here. Remember, this angle is also theta, and this angle is also theta. So draw in the directions of the components of the weight, parallel and perpendicular to the slope as well. Although it's really motion parallel to the slope that we're interested in at the moment. So we've got to find the acceleration and the tension in the tow bar. So let's have a look at using F equals ma. We're going to take up the slope, parallel to the slope, as the positive direction, and we're going to look at the forces on the trailer and the forces on the car separately. Let's start with the car. So the car has 2,500 newtons in a positive direction. We have T going backwards in a negative direction. We have 700 as well, which is negative, and then we have this component here, which is also negative, and that component there is 1000 g sine theta, so that's minus 1000 g sine theta. So just highlighting the components that we're working with in green so you can see all of those, and that equals the mass 1000 multiplied by the acceleration a, and of course we know that sine theta equals 1/20th, so that can be substituted in a second. That's equation 1. If we do the same thing for the trailer, then up the slope we've got T, and then backwards down the slope we've got minus 300, and then we've got minus 250 g sine theta, and that equals the mass 250a. So we then add equations 1 and 2 together, and that then gives us, so this then results in a equals 0.71 meters per second squared, and we can substitute that into either equation. I'm going to substitute that into equation 2, and that gives me T equals 600 newtons. We've got a positive value for T, which shows that we got the directions of T correct in the diagram. So question 9, we have a cyclist with weight 60 g, normal reaction, and her pedal power produces a forward force of 200 newtons. She's subject to air resistance and friction totaling 50 newtons, which would act in the direction opposing her motion, assuming she's accelerating up the slope. So part 1 requires us to draw a diagram showing the forces acting on the cyclist. We have done that. Part 2, what is the angle of the steepest slope that she can ascend? So I'm going to need to use F equals ma for this calculation. Choosing up as my positive direction there, I'm going to need to resolve forces here. Let's put in theta, and that's got to be 60g sine theta. Now, if the cyclist is just about able to get up the slope, then at this point the forces would be balanced. So she wouldn't necessarily even be accelerating, the forces would have to be balanced. So if the resultant force parallel to the slope equals 0, that means these forces here, the 200 up, would be balanced by these two forces coming downwards. So 200 would equal 50 plus 60g sine theta. Now that's the point at which the forces are balanced and the cyclist is essentially just about able to match the downwards forces with her pedal power force upwards. So she's not necessarily accelerating, she might be travelling at a constant speed up the slope. Now, if we rearrange and solve this equation, this gives me an answer of theta equals 14.7796 ... or 14.8 degrees to 1 decimal place. This is not the same as the answer in the back of the book of 13.2 degrees, because if you notice, the answer in the back of the book uses a mass of 67 kilograms rather than a mass of 60 kilograms, so I think this is a typo. If you actually do the whole problem and change this weight here to 67 kilograms, so a weight of 67g, then you do get the angle of 13.2 degrees. So this is an error in the textbook. I'm going to stick with the rest of the problem using the numbers from the question, so the 60 kilograms. So part 3. Cyclist is now cycling up a slope of 8 degrees, accelerating upwards. She's cycling as hard as she can, so the forward force must be 200 newtons. This time, if we apply F equals ma, going up, taking up as the positive direction, then we have 200 up the slope minus 50 down the slope minus, and this component here would be 60g sine 8. That must equal the mass 60 multiplied by the acceleration, which we're going to calculate. The acceleration then comes to 1.13610, which again is not the answer in the back of the book, but that's absolutely fine because we know we're working with a different mass of objects, so that's just 3 significant figures there. And we have to find the distance that she travels in 5 seconds. So if we set up our SUVAT information, S is what we're looking for, U we know is 5, V question mark, we don't actually need it, A is 1.1361, and T is question mark. No, we know that T is 5 seconds. So we can then work out S using S equals UT plus a half AT squared. So this gives us 39.2012 ... or 39.2 meters to 3 SF. Again, that's not the answer in the book, but it is the correct answer for this question. And part 4 wants us to work out what is her speed now. Well, we can use V equals U plus AT in order to calculate this. And that comes to 10.6805 ... so 10.7 meters per second to 3 SF. So question 10, we've got to draw the forces acting on the brick as they slide down the chute. So the weight of each brick is 3 kilograms, so weight 3g, mass of the brick is 3 kilograms, so the weight is 3g, and we have a normal reaction force acting on the brick like so. So we are told that the chute has a flat cross-section and smooth surface, so no resistance. Find the acceleration of the brick in part 2. So let's take the acceleration down like that. So that's our positive direction. Resolving our weight into 2 components using this triangle here. The only direction, again, that we end up having to work with is the horizontal, or the parallel direction, the direction of motion parallel to the slope. And actually, when we apply F equals ma, there is actually only one component here at work, so that's 3g sine 42 degrees, highlighted in green, and that equals the mass, which is 3 multiplied by the acceleration a, and this gives us a equals g sine 42, or acceleration equals 6.5574 ... so 6.56 meters per second squared to 3 significant figures. So part 3 says find the time taken for the brick to hit the ground. So we know S equals 10, U equals 0 if it starts from a rest, V question mark, and actually we don't need to find it out. Acceleration we've just calculated, and T is what we are indeed looking for. So this allows us to then use S equals UT plus a half AT squared. 10 equals, well, U is 0, so UT becomes 0. We've got a half multiplied by 6.557 ... multiplied by T squared. Rearranging this gives us T equals 1.7464, or 1.75 seconds to 3 SF. So, in fact, the chute is not smooth and the brick takes 3 seconds to reach the ground. Find the frictional force acting on the brick, assuming it to be constant. So I'm going to revisit my diagram up here and put in a frictional force like that. So we now know the brick takes 3 seconds to reach the ground. So S equals 10, U was equal to 0, it started at rest, V question mark, A question mark, T equals 3 seconds. So let's straight away rule out V, which we're not interested in, and then using the rest of these values, again, S equals UT plus a half AT squared, 10 equals a half A multiplied by 3 squared, so this allows us to work out the new acceleration, which comes to 20 over 9 meters per second squared. If we then resolve the forces acting on the brick using F equals ma, again taking down as positive, this time I'm going to highlight the 2 forces that run parallel to the slope that will contribute to the resultant force. 3g sine 42, that's this component here, remember we've used it already, 3g sine 42 minus F, going up the slope, is equal to the mass, which is 3 multiplied by the acceleration 2/9, and we can then rearrange this to work out the friction. Now I knew that the friction would be running up the slope because the particle is moving down the slope, and remember friction opposes the direction of motion, or the intended direction of motion. So this then gives me a frictional force of 13.0057 ... or 13.0 newtons to 3 SF. If the floor is smooth, the box cannot be in equilibrium in question 11 because there is a rope attached to the box and that is being pulled with a force of 100 newtons. So if the floor is smooth, there is no resistance opposing that pulling force, and the box will simply slide along the force being pulled along by the rope. Part 2. In fact, the floor is not smooth and the box is not in equilibrium. Draw a diagram showing all the external forces acting on the box. So let's add in the forces acting on the box. So we've got ATG, which is its weight acting downwards. We have a normal reaction force acting upwards. And then there must be a frictional force like this opposing the intended direction of motion, which is towards the right. Part 3 asks us to calculate the frictional force and the normal reaction of the floor on the box. So the box is in equilibrium, so that tells us that the resultant force is equal to 0. So if we look at forces horizontally, first of all, then this component here and this component here are what the 100 Newton force is divided into. So 100 cos 20, 100 sine 20 are the two components there. So we know that F is equal to 100 cos 20, balancing our horizontal forces. And vertically, we know that the normal reaction plus 100 sine 20 must be balanced by the ATG acting downwards. So this gives us F equals, and R, Newton and normal reaction equals, so the friction is equal to 93.969 or 94.0 newtons to 3 SF, and the normal reaction 749.797 or 750 newtons to 3 significant figures. So in the next part of the question, we now have the frictional force equal to 120 newtons, and we now have the box being pulled along by a tension force, and we don't know the value of this tension force, we just know that it's equal to T. So this component here becomes T sine 20, this component becomes T cos 20 degrees. We know the angle is 20 degrees. So part 4 says, calculate the force with which the rope must be pulled for the box to move at a constant speed. So constant speed implies acceleration equals 0, which implies the resultant force, which equals mass times acceleration, equals 0. So that tells us forces are balanced. So if we then look horizontally at the balanced forces, 120 left must equal T cos 20 right. So that gives us T equal 127.701 or 128 newtons to 3 significant figures. And in the final part of the question, we're told now that the box is being pulled with a force of 140 newtons. So let's change this to 140 over here, which means that these two components can also be changed to 140 sine 20, 140 cos 20, and we've got to calculate the acceleration. So the box is moving horizontally, so let's give it a horizontal acceleration like that. Going to the right is going to be positive. So I have 140 cos 20 going to the right, looking at this component here. This component here, sorry, this force here, the minus 120 frictional force going to the left, opposes that, and that equals the mass of the box, 80, multiplied by its acceleration a. So I'm back to using F equals ma because we're no longer in equilibrium. This gives me the acceleration, which is equal to 0.1444 ... so 0.144 meters per second squared to 3 SF. So question 12, we've got to draw in all of the forces acting on the block and the hanging mass. Well, the block has a mass of 5 kilograms, so a weight of 5 g newtons. There's a normal reaction like that, and a 15 newton force downwards like that, and then a tension force in the rope like that. Now the hanging mass has a mass of m, so weight of mg, same rope going round the pulley attaching the two particles together, so it has a tension force like that. So there's part 1, completed diagram. Part 2, the question tells us that the block is sliding up the plane at a constant speed. So constant speed implies acceleration equals 0, which implies resultant force equals 0. Forces are balanced. Let's draw in the components of the weight of the block on the slope. So that's 5g sine 30, 5g cos 30, like that. And let's look at the two objects in turn. I'm going to call the block on the slope A and the mass hanging on the end of the string B. So forces balanced on both of these. So for B, that tells us that tension equals mg, and for A, that means the components going up the slope, which is T, must be balanced by the two components going down the slope. So T must equal 15 plus 5g sine 30. We know T equals mg, so mg equals 15 plus 5g sine 30, and we can rearrange this to calculate the value of m. That comes to 4.0306, or 4.03 kilograms to 3 SF. We've also got to calculate the value of T. Remember to use the full accuracy of the value that we've worked out for m when we're calculating t, and t comes to 39.5 newtons exactly. Now, part 3 then implements an acceleration in the system. So that means that, let's say this is going to slide up the slope like that. This is going to move down the slope like that. And m is 6 kilograms. So that means this is 6g over here. So we're now applying F equals ma. We're going to start with object B and say down is positive. Object B has the heavier mass of the two, so let's assume B moves downwards and A slides up the slope. So down we have positive forces, that's 6g. Up we have negative forces, that's t. 6g minus t equals the mass, which is 6 multiplied by the acceleration A. And there we have one equation. Forces acting on A, the equation of motion, let's say sliding up the slope is positive. We've got t up the slope minus 15 down the slope minus 5g sine 30 also down the slope, and that equals the mass 5 multiplied by the acceleration A. And as has been the case in multiple such questions, we've got a positive and a negative t, so we can add together the two simultaneous equations. So we end up with 6g minus 15 minus 5g sine 30 equals 11a, and this then allows us to work out what a is. So the acceleration equals 1.7545 ... or 1.75 meters per second 3sf, and then substituting into either equation, if I use equation 1, tension equals 6g minus 6a, and make sure you use the full accuracy of your answer. The tension then works out to be 48.2727 ... or simply 48.3 newtons to 3sf. So in question 13, a sledge is found to travel with uniform speed down a slope, but then later on the same sledge starts from the bottom of the same slope with a speed of 2 meters per second. So there are two things going on here. Firstly, let's have a look at what's happening when the sledge is travelling with constant speed down the slope. So the sledge must have a mass, m, kilograms, so a weight, mg. There must be a normal reaction. And we're accelerating down the slope. Well, actually, our acceleration is 0 because we're travelling at a constant speed. And let's put in a frictional force that we are going to have to try and find the value of. So my components of my weight look like that. So this is mg sine theta, mg cos theta. There's no forward force, it's just a sledge. And remember, constant speed tells me acceleration equals 0, tells me my resultant forces are equal to 0. My sum of my resultant force is 0, forces are balanced. So looking parallel to the slope, that tells me F must equal mg sine theta. So that's the size of my frictional force. So in the second part of the question, the sledge is pushed up the slope with a speed of 2 meters per second. So that means we are pushed up the slope, starting here with a speed of 2 meters per second. So we have to work out how far it travels up the slope before coming to rest. So let's say the acceleration is in that direction there. So the resistance force is now going to change direction, but presumably still take this value here. Now my components of my weight look like that. Again, mg sine theta, mg cos theta, and we know a little bit about sine theta as well. We're able to use that in a second. So this time, if I use F equals ma, taking up the slope as positive, well, I have no components going up the slope, but I have minus F minus mg sine theta equals ma. So that's minus mg sine theta minus mg sine theta equals ma. So that then gives me a equals negative 2g sine theta. And of course, I can then use this value of theta up here. So that's minus 2g over 50 or minus g over 25. So I've now got my acceleration. And how far will the sledge travel up the slope? Well, S is what we're looking for. U is 2. We were told that we start at 2. V is 0 because we're travelling to rest. A is minus G over 25, and T question mark, and we don't need to calculate the time either. So we can then use from here V squared equals U squared plus 2AS. 0 equals 4 plus 2 times minus G over 25 multiplied by S. And make sure you don't get your S confused with a 5. That's an S. And rearrange your CVAT equation. S equals 5.102, so 5.10 metres to 3 SF. Okay, so what do we know about this train? It has a mass of 200 tonnes, so that's 200,000 kilograms and a weight of 200,000 G. Normal reaction acting perpendicular to the slope as this direction shows. The driving force is 25,000 newtons, and then the resistance force is a constant 10,000 newtons. So let's put in the components of the weight as follows. So that angle is theta, and then we can work out the components as we need them. So we are going to use F equals ma, taking up the slope as positive, so acceleration in this direction here. What are the components that I need to look at? This one, and this one going down the slope. So up the slope I have 25,000, down the slope 10,000, minus 200,000 G sine theta, so that's this component here, and that equals the mass, which is 200,000 multiplied by the acceleration. I know that sine theta equals 1/50th, so I can sub that in here, and then working out the acceleration, this comes to minus 0.121 meters per second squared, which makes sense, it's decelerating. So we have to show that the train comes to a standstill after climbing for 413 meters. So if we say S equals question mark, U equals 10, V equals 0 because we're coming to a standstill, A equals minus 0.121, T equals question mark. Let's lose the T, we want to find S, and V squared equals U squared plus 2AS. So 0 equals 100 plus 2 times minus 0.121 multiplied by S. Again, make sure you don't confuse S for a 5. And this gives us S equals 413.223, which is 413 metres to 3 SF as required. So let's have a look at the railway truck. Now we have a mass of M, unknown, so weight of mg, normal reaction nr. There is presumably some sort of frictional force, which we'll call F, and it's just running down the slope, so we're assuming we don't have, and it's a railway truck, not an engine, so we don't have a driving force. Let's put in the components like so. This angle here, theta, so mg sine theta, mg cos theta. And we know that the speed was a constant 5 meters per second on the slope. So on the slope, that means speed is constant, which implies acceleration equals 0. So that means the forces must be balanced, which means that this force here must be balanced by this force over here. So we know resultant force equals 0. So looking at the forces parallel to the slope, F equals mg sine theta. And then we know the resistance is unchanged, so the truck travels down onto flat ground here. So that means if we look at the forces acting on the truck on flat ground, we've got mg, we've got the normal reaction, and we've still got the friction, which is equal to mg sine theta. So let's now assume, because it's travelling on the flat ground, that we've got an acceleration. So on the flat ground, let's apply F equals ma going to the right as positive. So of course the force of gravity and this component here pulled the truck down the slope, and it had velocity and it had constant velocity as it travelled down the slope. The friction tried to oppose the motion, which meant that we had a constant speed rather than an acceleration. But when we hit flat ground, that component of the weight isn't there to pull the particle along any further because it's now on horizontal ground, so eventually it will just decelerate to a halt. So we need to find out what this deceleration is. So the only horizontal force acting is this. So we know that that's in the negative direction, so minus F equals m times the acceleration a. F, remember, was unchanged from here, so that's minus mg sine theta equals ma. M's cancel, and we know sine theta is 1 over 250, so a equals minus g over 250 metres per second squared. Now, how far will the truck run for? Well, it will run until it stops. So let's fill in our SUVAT information. S is what we're looking for. U equals 5, V equals 0, A is minus G over 250. T we don't actually know and can't use. So V squared equals U squared plus 2AS. So 0 equals 25 plus 2 times minus G over 250 multiplied by S, which gives S equals 318.87 ... so 319 meters to 3s.